Okay, welcome everyone. We are very excited to have Avishay Tal speaking at our TCS Plus seminar today. He's an assistant professor at Department of EECS at UC Berkeley. He has seminal works in many areas of complexity, including circuit complexity, pseudo-randomness, quantum complexity, and Boolean analysis. Today, he will talk about his recent paper on junta approximation, distance approximation with co-authors. Regarding questions, please feel free to unmute yourself and ask questions. I'll also monitor the questions in the chat, so you can write them there, and I'll convey them to Avishay. Also, I request you to keep your videos on if possible, as this makes it a bit easier for the speaker. Okay, over to you, Avishay. Thanks.
Thank you, Somega, for this wonderful introduction. Yeah, so it's really a pleasure to be in TCS Plus again. This is a joint work with Vishnu and Michael, really two wonderful students from Berkeley. Okay, so this is about junta distance approximation. And in particular, this is a talk about probability testing. So let's start with some background. So probability testing, it's a widely used notion. You're given some query access to, let's say, a Boolean function f that sits inside a black box, and you can query this black box on any particular input, and you want to distinguish whether the function has some property pi, or whether the function is far from having the property pi, mainly meaning that it's epsilon far from every function that satisfies pi. So really, pictorially, you can think of it as if you have pi, which is like a collection of functions, and this is like the green circle, and on the green circle you should answer yes, and if you're epsilon far from the green circle you should answer no, but if you're in between, then you're allowed to do whatever you want. So there is some gap here. Okay. So let's talk about junta testing. So this is one of the classical problems that was studied in probability testing. A function is called a k-junta if it depends on at most k coordinates, or more precisely, that you can write f on x1 up to xn as g of xi1 up to xik, where i1 up to ik are some k coordinates. And why is it a natural and useful notion? Well, it comes out very naturally when we think about feature selection in machine learning, right? So if we think about some function and we see a lot of properties or a lot of attributes, in many cases, most of these attributes would not affect the result of the function, and we really want to identify the important features that matter. Right, so this is a widely useful notion in machine learning. And it was also motivated by PCPs and works on the long code testing. Okay, so let me spell out what do I mean by k-junta testing. So this is just applying probability testing to the case of k-juntas. So we really want to distinguish between two cases. In the yes case, the function is a perfect k-junta. And in the no case, the function is epsilon far from any k-junta. Okay. So this is a very well-studied problem in probability testing, and it was introduced by this work by Fisher et al. And a long line of work followed, and by now we know the optimal upper and lower bounds for this testing problem. We know that we can test whether a function is a k-junta with order k log k queries. This is due to a work of Eric, who is on the call, so hi Eric. And the lower bound, which matches this upper bound, shows that you need at least k log k many queries. Okay. And notice that the number of queries is independent of m. So if we think of k as like maybe a constant, then we just need to make constant many queries in order to know whether the function is a k-junta or far from it. So there's no dependence on the ambient dimension n. So that's very intriguing and very nice. And we would have the same property also to our result, But our result would have a much worse dependence on k. So let's talk about that next. So it seems that in the standard notion of property testing, we understand how many queries we need in order to test whether a function is a k-junta. But we can relax this notion, and this is maybe more motivated from practice, and say that, right, so sometimes we are not getting things that are perfectly k-juntas, but we are getting things that are, up to some small noise k-juntas. So what would happen if we are, in the yes case, we are getting things that are somewhat close to the property, and in the no case, we are getting things that are farther away from the property. Okay, so this is the notion is called tolerant property testing. Can be distinguished between things that are epsilon prime close to pi or things that are epsilon far from pi. Okay, and there's a gap between epsilon prime and epsilon, so there's still this white area for which you can answer whatever you want. Okay, so it turns out that for this task we know algorithms, but they have much more queries. So Blais et al. Gave a tester that makes exponential in k many queries and can tell the difference between things that are epsilon over 16 close to a k-junta and functions that are epsilon far from a k-junta. Okay. A recent result by Mossel and Neeman gave, again, an exponential in k tester that can tell the difference between any two parameters. Like you can pick C and epsilon to be any two parameters, and you can distinguish between the yes case where the functions are C minus epsilon close, and the no case where functions are C far. Okay, so notice in particular that the result of Blais et al., you have a multiplicative gap between the closeness and farthest parameters. In the DMN result, you don't have it. So you can sort of pick, C to be, 0.2 and C minus epsilon to the 0.19, for example, which you at least cannot do from the first result. And more accurately, what DMN did is that they output an estimate to the distance of your function to the best k-junta. Okay, so you get a function which is not necessarily a k-junta. There is a junta that let's say is C far from your function, and you need to output a number which is relatively close to C. Okay, so an approximation for C. Okay. On the other hand, let's talk about lower bounds. Levy and Weingarten showed that non-adaptive testing requires at least k-squared many queries. And PRW showed that, in fact, you need exponential in nearly square root k many queries if you want to distinguish between these two parameters. In the yes case, you are 1 over k to the 0.51 close to a k-junta. And in the no case, you are 1 over square root k far. Notice here that the closeness and farness parameters depend on k, whereas in the result of Levy and Weingarten, there were absolute constants. Okay. So this is a brief summary of some results known about this setting. Notice that in these settings, the upper bounds are only exponential in k, and whereas in the previous setting, it was nearly linear. Let's just mention that this setting is maybe more motivated from practice because, for example, think about the feature selection task. It seems very natural that our function would depend on a few coordinates, or at least would be very correlated with something that depends only on a few coordinates, but it's more unlikely that it's perfectly described by just these k coordinates. So for example, for the motivation coming from machine learning, it makes more sense to talk about the tolerant case. Okay. Our main theorem is that we get a tolerant tester that makes exponential in square root k many queries and can tell the difference again between any two parameters to your choosing, whether the function is c minus epsilon close or c far from a k-junta. More precisely, we return a number alpha, such that alpha is a good estimate, is an epsilon additive estimator for the maximal correlation of f with a junta g, where g ranges over all k-juntas. Okay, and notice that to estimate the best correlation is up to linear transformation, the same as estimating the distance to the function. Right? The distance of f and g, right, is a linear, can write it as 1 minus twice the correlation or something like that. Yeah. Okay, so
Avishay, is this so there is some, it's worse dependence on epsilon than the previous papers, is it?
Yes. So that's correct. We didn't actually try to. We put more emphasis on the dependence on k, and yeah, our dependence on epsilon is worse, and this is due to one bottleneck in the argument. On the other hand, yeah. So if we want to, we can also get the dependence exponential in k and logarithmic in polynomial in 1 over epsilon, but that's we view epsilon as a less important parameter than k for our purposes. Yeah, but that's correct.
So in all of these works, is the notion of distance the same, like the L2 kind of distance, or are there other notions of distance that are studied?
So when I say close and far, I'm talking about Boolean functions. So I just mean how many what's the fraction of inputs on which we differ. Okay. So that's the notion of a distance. Does it answer your question? Okay, good. Okay, so this is our main result, and I guess now we'll dive more into the ideas and the techniques. So our work is really built on top of the techniques of DMN, and their main idea was a notion called a coordinate oracle. What's a coordinate oracle? A coordinate oracle to coordinate I is just a function that given input x, just output xi. Now this seems rather trivial. Like if you know I, then it's really not a problem to generate this coordinate oracle. But the point is that we would get it without even knowing the coordinate. So we would get so DMN gets this set of coordinate oracles, but without even knowing what the coordinates are. So what do I mean by that? So given x, let's say the oracle O1 talks with the black box function f and outputs xi1. Okay, you don't know what I1 is, but you know that it outputs a consistent coordinate from x. And what you really want, the coordinate oracles to be coordinate oracles to the junta variables, right? If you would have it for the junta variables, this would put you in a good place. So this is more or less the idea. The idea of DMN is that they give a procedure that makes a polynomial in k over epsilon many queries and produces approximate coordinate oracles to a set of poly k over epsilon many coordinates that are suspects. These are the coordinates for which we think the variables of the junta sits within this set of coordinates. Okay, so notice that if indeed the variables of the junta sits inside this set S, this set of L coordinates, then we are in good shape because we are in some way reduce the number of coordinates from n to order k squared. Okay, again, I'm sort of ignoring dependence on epsilon throughout the talk. I'm putting more emphasis on k. Okay, so for me to explain to you more about what are the suspects coordinates, I want to dive a little bit about Fourier analysis and give you a brief recap about Fourier expansion. So this is a very well-known and widely used tool in analysis of Boolean function. You can write every Boolean function in the Fourier basis. This is called the Fourier representation or the Fourier expansion. So there's a unique way to write f of x as a multilinear polynomial, where you have a coefficient f ad of s for every subset of the coordinates, and you have this coefficient is multiplied by a monomial, right? So let's give an example. Let's say that you take the maximum of two variables, and I claim that as a polynomial, you can write it as the following polynomial, and you can check my claim, just, you know, assign all possible 4 values to the inputs and see that the value of the function agrees with the value of the polynomial, okay? Okay, and there are a lot of nice features about this representation. So in particular, we can calculate these coefficients efficiently, or at least estimate them if we have access to the function f, because these coefficients are just the expected value of f of x in a product with you know, x to the s, or this monomial. So in particular, if we get samples, we can just take the empirical mean, and this will give us a good estimate for the Fourier coefficient. Okay, that's one nice thing about the Fourier coefficients. Another is that, you know, when we take the sum of their squares, it equals the expectation of f squared. If f was a Boolean function, f squared is always 1. So this means that the sum of squares of Fourier coefficient equals 1. One way to view it is to say that the Fourier coefficient squares is a probability distribution over subsets, okay, because it sums up to 1. Another natural notion, the variance of a function can be written similarly as the sum of squares of non-empty sets. And a very important notion in analysis of Boolean function, the influence, which captures the probability that if we flip the ith bit, we are changing the value of the function. This can be written as a sum of squares of sets that contains the coordinate I. Okay, and if we take the total influence or the sum of all influences, well, every set is summed up, you know, by its cardinality. So we really get this very nice expression for the total influence. And similarly, we can talk about you know, more refined notions where we look at influence up to level k and total influence up to level k. And this is just summing up over all sets of size at most k. And then we have an upper bound on the total influence up to level k, which is at most k. Right, so these are a few useful notions in when you look at the Fourier representation. So what DMN shows is that this is a good set of suspects, okay? So look at all coordinates whose annotated influence up to level k is at least epsilon squared over k, okay? So these are in some sense coordinates such that if you flip their value with some non-negligible probability, you're changing the value of the function, okay? So the lemma, which is really, you know, a few lines proof, is that if G was the best, you know, the best k-junta, the one that maximizes the correlation with F, and G was supported on a set of coordinates T, then there's another junta, G prime, that is supported on T intersection S, such that the correlation of F with G prime is at least as good as the correlation of F with G minus epsilon. So in other words, what does it tell us? It tells us that if we, instead of looking at the entire n coordinates, we are just looking at the coordinates inside S, the best correlation there is more or less the same. We are only losing epsilon. And this is really, you know, it's a simple exercise that involves like Parseval identity and like maybe a Cauchy-Schwarz inequality at some point. So this is not too complicated, but I will not show that. So that's good. And moreover, and that's more challenging, yeah, what DMN show is that they can grant coordinate oracles to this set S. okay, so I want to note a few things. So one is that this set is not that big. The size of the set S is at most k squared over epsilon squared. And why is that? Well, let's just look at the sum of influences up to level k. On the one hand, it's at most k, and on the other hand, it's at least the size of S multiplied by epsilon squared over k. Okay, so this means that together, right, together we get that the size of S is at most k squared over epsilon squared. So DMN showed that there exists a query algorithm that makes poly k over epsilon many queries, and it yields coordinate oracles such that the number of coordinate oracles is order k squared over epsilon squared, and every coordinate in S is covered by one of these coordinate oracles. Okay. So notice that I'm not saying that the oracles will be precisely to the set S, because in particular, it could be the case that, you know, for some coordinates, the influence would be very close to the threshold. And then it will be hard for me to decide whether the coordinate is inside S or not. So that's exactly why we don't have this stronger guarantee, but we have a guarantee which is nonetheless still useful. And that is that we are getting the set S in addition to maybe order k squared over epsilon squared additional variables. Okay, so overall we are like getting poly k over epsilon many coordinates. Okay, so why is it useful? Why is it useful to get coordinate oracles? Well, one thing is that, right, so if I'm now sampling a random input, then I just see the projection of the coordinate oracles to the interesting variables. So I can see like random samples of inputs and output to the function, right? Like to the underlying function, the function from L bits to 1 bit. But the first idea that we had is that it would be nicer if we could have, instead of sample access to, you know, to these L coordinates, if we can have query access to them. So what if I want to specify, you know, values to these L coordinates, and I want to, you know, get an input X that is consistent with these values, and otherwise is completely uniformly random, right? So the vector X is on n bits, and I want to specify L coordinates out of it, and I want these L coordinates to be fixed to these values, and everything else I want to be completely random. Okay. If I can do that, then in particular, I can estimate the following expectation. You know, what's the expected value of f of x condition on, you know, these L coordinates equal a specific value, right? So notice that why is it useful? So if these are indeed like if let's say f is indeed a junta that depends on these L variables, then for every fixing of these L bits, I would have that the expected value here is either +1 or -1. So this would give us a nice way to know that we are right. And if it's approximately a junta, then we'll see that for many of these values, the expected value is bounded away from 0. Okay.
A couple of questions.
Yeah.
So the first thing is, the algorithm by DMN, it gives coordinate oracles, but it does not tell you like which coordinates are in
exactly.
And then, but it's able to give you like, so like OI is not equal to OJ for any I not equal to J.
Yes. Yes. Yeah. And this is you can do some kind of cleanup, and you can sort of make sure that the coordinates are not equal. You can just check. One way to do it is you just check the difference between two coordinates, right? So if they are the same, then they would agree on all, and if they are different, then they would differ on half. So you can do this cleanup later, and you can also. So another thing that I sort of hide beneath the rug is that these are not perfect coordinate oracles, but approximate. But since this is, you know, these are approximate dictators, you can always do like local decoding, and basically you can get like a randomized algorithm that for every input is correct with high probability. So therefore, you can just ignore it and think of it as if for every input it gives you like the right answer. because you can also take this high probability arbitrary close to 1.
And how do you do the sampling?
Yeah, so that's what I'm going to show next. Yeah. So that's a very cute idea. So how do you do it? I want to sample a random x, under this condition. So let's just sample a random x to begin with, right? So that at least satisfies that it's uniformly random. But of course, with high probability, we will not satisfy the condition. So as long as we are not satisfying the condition, we are apply some noise to x. So what do? We take x prime to be a copy of x, where we flip each bit independently with probability 1 over L. Okay. And we check if the distance of the oracles applied to x prime, this L bits is from B is smaller than the distance of x to B, then we move from x to x prime. Okay. And if not, then we try again. Then we, apply another set of noise and we try again. Eventually, when this external while loop would end, we know that the oracles equals D, and then we just output X. And the simple claim is that this algorithm halts in expected polynomial time in L, and it produces a uniformly random X under this condition. And the reason that it runs in expected time polynomial in L is the following. So think of it as follows. So if you are not in the case where the oracles output B, then you know that at least one coordinate is wrong. So the probability that now you would flip this coordinate and not flip all the other coordinates is at least a constant over L. So if this happens, then you are improving your distance, and this happens with probability at least constant over L. So in expected time order L, you would improve your distance. So overall, in expected time order L squared, you would get there. So this is a very simple algorithm. And notice that what it gives us essentially, in some sense, we can just now forget about all the other coordinates and just think of the L coordinates as our input coordinates, right? We don't know their identity, but in some sense we can specify inputs to them, and then we get a random output to the function under this condition that these inputs equals these specific values. So it gives us an oracle access to a randomized function on the L coordinates. If the function was indeed an L junta, this would be a deterministic function. But since the function is only correlated with an L junta, then for some of these assignments, we would get like a random bit that is maybe biased towards 1 or biased towards 0, and maybe even unbiased in some cases. Okay, so in some sense, from now on, I'm just gonna think of my function as now a function on L bits, and because I have this implicit access to it, I can do everything on functions on L bits. Notice that now it's not necessarily a Boolean function, but we can think of it as a randomized Boolean function or a bounded function, meaning a function that gives for every specific value, let's say a number between -1 and 1, which is like the bias of the function condition on these values. Okay. So our second idea, so our first idea was to give this implicit access. Our second idea was how can we reduce the number of oracles from k squared to k? So recall that DMN essentially gave coordinate oracles to all these coordinates in S. But there could be k square of them, right? How can we reduce their number to order k? So the main bottleneck and the main reason why the size of S could be as large as k squared is that the sum of the influences could be k. and each one is contributing at least 1 over k. And we cannot, if we are making this 1 over k much bigger, then we are actually losing something important. So we cannot take coordinates that have very large influences, much larger than 1 over k. So motivated by the fact that there is some kind of that the sum of influences could be much larger than 1, we were thinking, how can we come up with a different notion such that the sum of this new influence or normalized influence would be at most 1. Okay, so after some trial and error, we came up with this notion that's called the normalized influence. So the normalized influence of coordinate I is the sum of squares of the Fourier coefficient that contains I divided by the size of the set. Okay, in some sense, we are, notice that the regular influence is the same, but without dividing by the size of the set. So intuitively, we sort of penalize bigger sets, and we give more weight to Fourier mass that come from smaller sets. Okay. And similarly, we define the normalized influence up to degree k, where we are just summing over sets of size at most k. Okay. So now I'm going to tell you a few properties of these normalized influences. Okay, so this is a definition again. And the first claim is that indeed the normalized influences sum up to less than 1. And this is really a one-line calculation. You can see that when you sum up all the normalized influences of a function, now I think of functions from LB to the reals, then this equals the sum of squares of the Fourier coefficients over all non-empty sets. Okay, because notice that every set contributes its cardinality multiplied by 1 over its cardinality to this sum. So it contributes 1, except for the empty set that doesn't contribute at all. Okay, so what does it mean? It means that, let's say if the variance is 1, like if the function is balanced, then really the normalized influences define a probability distribution over coordinates. And if the variance is, smaller than 1, then it's a sub-probability distribution, right? These are positive numbers that sum up to less than 1. Okay, so that's nice. And the second claim is more about k-juntas. It tells us the following. So recall, we assume that there is some function g, which is a k-junta on, and this function depends only on the coordinates inside T. And let's think of G as like the best junta that correlates with F. And so in particular, we can assume that the best correlation is at least a constant. Okay, otherwise the task becomes trivial, what we are trying to do. So then you can show that the sum of normalized influences inside T is at least a constant. Okay, and this is again a simple proof. You just look on all coordinates inside T, and then you look at the normalized influence of this coordinate I, and then you notice that for any set S that is contained in T, you are counting it times. Okay, so things that are contained slightly in T maybe are counted several times, but I'm not going to take this into account. So a lower bound on the sum of normalized influences is at least the sum of squares of sets inside T. And there's a nice connection. If we know that the best correlation between F and G is C, then we know that this sum of squares is at least C squared minus the Fourier coefficient of the empty set squared. And this is also like, a few lines of calculation. So in some sense, you can think of this sum of squares inside T as some kind of an approximation to the best correlation between F and G. And we get that the sum of normalized influences is lower bounded by the sum of squares. Okay, so now that we have these two claims, it seems that normalized influences are quite useful, and the main challenging thing that we do is that we show that we can estimate these normalized influences up to a multiplicative constant factor in polynomial in L many queries. Okay, so let's now see how to combine what to do with all these three things. So we have the normalized influence sum up to less than 1. The normalized influence inside T is at least a constant. And we can also estimate the normalized influences. How can we take advantage of all these two claims and this lemma? Well, a simple algorithm comes to mind. Let's just estimate all these normalized influences. Okay, we have L coordinates. So notice that L is polynomial in K, so we can actually run in times that is polynomial in L, so that's fine. And we couldn't do it initially because N, we didn't want any dependence on N, but once we reduce the dimension from N to L, then we can do it, we can do something brute force over all coordinates. We sample a coordinate I now with probability that is lambda I over the sum of lambdas. And these lambdas are, think of them as like good approximation for the normalized influences. Now, what would happen when we do it, when we sample like that? If indeed, we have a good junta that depends on coordinates in T with constant correlation, then we would sample a coordinate from in T, we would sample a coordinate inside T with constant probability. Notice that initially we have K squared coordinates, so sampling a coordinate inside T would happen with 1 over K probability. When we do it with this sampling algorithm that puts different weights to different coordinates, we are sampling a coordinate inside T with constant probability. Okay. And notice, of course, we don't know T. That's a problem. Like T was this hypothetical best set of coordinates for which we have the best junta on. How can we make it into how can we make it into an algorithm that reveals all the coordinates? Well, we just repeat sort of recursively, and we repeat this sampling process order k over epsilon squared time. Every time, if we already reveal some coordinate, we picked some coordinates, we are sort of, we already make a decision about them. So we are going to randomly restrict them to randomly chosen constants. Okay, and once we do that, then this allows us to do the recursion. And what we'll get is that after this many steps, either we cover all of the coordinates in T, this special set that indeed contains the best junta, or we cover a subset T prime of T, such that the best junta on T prime is more or less like the best junta on T, right? So we are losing at most epsilon. Okay, so it could be that some of these, that once we revealed a lot of these coordinates, we are not getting much more from the remaining coordinates. So that's okay. We just need to output an estimate. Okay. So overall, what did we get? We got an algorithm, and so far everything worked in polynomial in K over epsilon. And it gives us an implicit access to order K over epsilon squared coordinates such that the best correlation of F with a K junta is similar to the best correlation that F has on a K junta on coordinate inside S prime. Okay. And moreover, we now have implicit access to these coordinates and oracle access, so we can estimate the best correlation that F has with the best junta on S prime. Okay, so notice that this is not exactly what we were setting up to achieve, because we are sort of here assuming that there exists some good junta on K variables, and we are getting a set of order K coordinates for which we have a good junta on. So there's a mismatch between how many coordinates we are looking at, right? So we went from K to order K. Right. But I would say that, probably for more practical applications, this is the more interesting algorithm because it runs in, in polynomial time. Okay, how do how do we reduce the number of coordinates even further? How do we get from order k coordinates to k coordinates? That's the next question. Okay, so the idea, the main bottleneck in the previous argument was the following. Every time we sampled one coordinate, and with constant probability, this coordinate was in T, right? So, after order k coordinates, by Chernoff, we cover T. But what if we don't want to get any coordinate outside T? Like, what would be the probability that this happens? Well, the chance that all these k samples would fall inside T can be exponentially small in k, right? Because everything, every sample is inside T with constant probability. So it seems that, we could get an exponential algorithm in k that finds T exactly, but it will be exponential in k, and this was already known. So that's not new. So instead, we're thinking, what if we could sample more than one coordinate at a time? And this naturally brings up the notion of a normalized influence of a set of coordinates. So for a set of coordinates U, you just look at all the sets S that contains U, and you look at the sum of squares of them, of the Fourier coefficient, divided by S choose U. So you can think about it as if, S is spreading its mass to all subsets of, let's say, a particular size, and it gives mass, 1 over S choose U to each one of them. Okay, so what can we say about normalized influence of a set? Well, it's very similar to normalized influences of coordinates. Their sum is at most 1, and their sum inside T, if T is this good set, is at least the sum of squares of sets S that are inside T and are of size at least U. Another lemma, which is, again, takes more work, is that we can estimate these normalized influences of sets. And combining these estimates, we can actually sample the set according to these normalized influences. And what we would get that, as long as T captures a lot of the Fourier mass of F, at least constant fraction of it. And moreover, we need this Fourier mass to sit on levels that are higher than square root k. Then we would sample a subset U inside T of size square root k with constant probability. So now in every sample, we would get square root k coordinates that all of them are inside T with constant probability. But notice that in order to do this estimation, I needed to really estimate the normalized influence over all subsets of size square root k, and I have 2 to the square root k of them, or roughly maybe k to the square root k of them. So maybe more pictorially, so this is a lot of notation. So think of this as your set of coordinates. This is like maybe 1000 k coordinates, and you want to find k coordinates among them that are the important ones. And every time, and we have this unknown set T that is really the set that you're trying to figure out. What we show is that every time you can find like square root k coordinates with constant probability inside T, and then you can recurse. So once you found them, you can try again, and with constant probability, would find another square root k, another square root k, so on and so forth. So the probability that you would be successful in all these trials is like constant raised to the power square root k, right? Because you need only square root k parts in order to cover T. So now we increase the probability of success from exponentially small in k to exponentially small in square root k. And this works well, but there's like one caveat, and this is, we assume that the sum of squares inside T on the higher levels is high. What would happen if it's low? then we have no guarantee, right? Then we don't really guarantee that we were sampling something inside T. So how can we handle this case? So it turns out that in this case, like, if I tell you what T is, then there's a very nice expression to what is the best junta that is correlated with F that is supported on coordinates in T. And this is just that you take the Fourier expansion only on sets contained in T, and you take its sum. Okay, so that's the best junta inside T that correlates with F. And therefore, the expected value of F inner product with G is just the expected value of this absolute, the expected value of the absolute value of the truncated sum. And so this is really a simple thing. Maybe I could have explained it more carefully, but it's really like a few lines of calculation to see that this is indeed correct, the first line. And then you write this this internal sum, you write it as a sum over small sets and sum over large sets. Okay, so think of it as like the low degree part of the function and the high degree part. The things of degree at most square root k and the things of degree bigger than square root k. And by the assumption on T, you get that the high degree terms are actually, you can think of them as some kind of error term that is of magnitude at most epsilon. So really, to estimate the correlation of F and G, where G is some junta on T, on the coordinates inside T, it's enough to estimate the sum over coefficient of size at most square root k. And how can you do that? Well, first, you can estimate all Fourier coefficients of sets of size at most square root k without knowing T. And then you can iterate over all potential sets T and calculate this thing. Once you have the estimates for the Fourier coefficients, the second step need no further samples. You just can calculate it from the Fourier coefficients themselves. So once you do it, you can figure out which set maximizes this quantity, and this would be the set that you're choosing. So I'm lying a bit, because it could be that for our good set T, this happens, but for another set U, this doesn't happen, and then I don't have this guarantee. So we need to worry about this, and we applied some noise. And there are some details that I'm hiding under the rug, but this is the picture that we had in mind, and we ran into some difficulties, and we were able to solve that. Okay, so notice that our algorithm runs in exponential in k time, because we are iterating over all sets in the end, but we are reusing the queries. Like we are using exponentially square root k queries in order to estimate all small Fourier coefficients, and then we just reuse it for all potential sets T. So overall, this gives us an algorithm that can estimate the best correlation between F and G. Okay, so let me just recap and mention a few open questions. So to recap, we give a tester that makes exponentially square root k over epsilon many queries. Now, the dependence on epsilon is really because of the steps that I didn't mention, which is applying the noise operator. It might be nice to get a much better dependence on epsilon, and we've given it a little thought, but not much thought. And we return a number alpha, such that alpha is an additive approximation for the best correlation of F with a k junta. And along the way, we get implicit access to the underlying junta that is specified by a set of coordinate oracles. And I think this is of independent interest. Like this could be used later, like, for example, if you want to do testing for subclasses of juntas, or if we want to do learning. And I think that some of these ideas were also appeared in the work of Nader Pshuti, although it was not in the tolerant setting. It was in the non-tolerant setting. Okay, let me mention a few open problems. The first is about running time. Our running time is exponential in k. Our number of queries is exponentially square root k. Can we get our running time to be better than exponential in k? And in fact, we believe that there is an inherent difficulty here because it seems that the problem of finding the best k-junta is somewhat related to hardness of approximation results, but we were not able to show it quite yet. The second question is about adaptive versus non-adaptive testers. And an intriguing fact is that our upper bound was exponentially square root k, and the non-adaptive lower bound of PRW was also exponentially square root k. But of course, there's a mismatch. Our tester is adaptive, their lower bound is for non-adaptive testers. So two natural open questions: can you improve the lower bound to work for adaptive testers? And can you improve the upper bound to not use adaptivity? Okay, so these are two interesting follow-up questions. And third is about quantum testers. And actually, quantum testers were an inspiration for our techniques. In particular, if you have a quantum tester, you can sample from the Fourier distribution. So you can sort of sample these sets U efficiently. You don't need to do it in time which is exponential in square root k. You can do it in time which is polynomial in k. So at least for one of the, our algorithm is composed of two steps. So for one of these steps, we can improve exponentially the running time. But for the second step, we don't know how to improve at all. Like when the function depends on only the low degree part, we don't know how the quantum tester would work faster. And so it means that maybe so quantum testers might be useful because they allow us to sample from the Fourier distribution efficiently, but we need more ideas in order to get better algorithms for tolerant testing in the quantum setting. Okay, that's all I had to say, and I'll be happy to take further questions.
I have a question. I just wanted to make sure I understood. So in the last step, when you're going through all possible subsets T, like to compute the Fourier, the second part. So yeah. Does that mean that, at the end of this, you actually know what the set T is of coordinates on which your function depends?
Yeah, but notice that at some point in my slideshow, I sort of said, from now on, I'm instead of looking at n coordinates, I'm looking at L coordinates. And out of these L coordinates, I would know which k are the good k. But notice that the L coordinates, I don't really know what do they correspond from the initial n coordinates. So in some sense, I would know which of the coordinate oracles are the ones that I care about, but I would still not know which coordinate they are. So in some sense, like once we did this, you can think of the first step as some kind of dimension reduction. We are going from n dimensions to order k dimensions. And now we can do things that even depend on the dimension, right? Because we are looking for things that work in time which is polynomial in k or sub-exponential in k. So in particular, right? So it's kind of intriguing. It seems that the problem of k-junta testing is most interesting when k and n are linearly dependent. So really, this fact that I said earlier, that the fact that the tester should run in time that is independent of n, you can just forget about it because we already took care of this part when we did this coordinate oracles and dimension reduction. And now you can run in time which is depends even on n, and it can be, in some sense, we are doing an algorithm that works in sub-exponential in n time, but n is linear in k for us, or L. Okay, we called it L. Right, so, yeah.
So what's the best adaptive testing lower bound right now? And like, what's the best like non-adaptive testing upper bound, I guess?
It's a good question. I think probably some people in the audience would know better than me. Michael, do you know the answer?
I don't know of any adaptive lower bound for the tolerance setting. There's certainly some for the non-tolerance setting. And in terms of non-adaptive algorithms, I'm not sure if Eric's algorithm is non-adaptive or not. I can't remember off the top of my head, but that might be the only one that might be non-adaptive.
Yeah. Yeah, it's a good question. I mean, it seems plausible to me that some of these algorithms that works in time exponential in K could be made non-adaptive. We even have ideas how to make our algorithm somewhat non-adaptive, but in some settings. But this is still a work in progress, so we don't know yet. So notice that one notion is very adaptive in some algorithms that I presented was very adaptive, and this is this algorithm that gives you Oracle access to the underlying junta, this implicit access, right? Because in some sense we are like applying some noise, and then we check the values, and if these are values that gets us closest to our target, then we make the step. So this is highly adaptive. Like it's not clear how to simulate this algorithm using non-adaptivity. Yes, so this part of the algorithm is very adaptive. And there's another part that is adaptive, and this is the fact that we are sort of picking these coordinates one at a time, or like one subset at a time. But every time that we pick a new subset, we need to sort of restrict the previous bits that we already picked. So this is also adaptive. And it's not clear if this can be made non-adaptive. Eric, do you know any of any non-adaptive lower bounds that are maybe better than linear in K?
No, I think just like this trivial connection between non-adaptive and adaptive, like the exponential loss, like, or just the non-tolerant version, those are the only lower bounds I'm aware of.
Okay. Yeah. Yeah, and I should say that these non-adaptive lower bounds fail in the adaptive case. Like if you have adaptivity, even 2 rounds of adaptivity, you make queries, you see what you get, and then you make another set of queries, you can break the hard instance very, very quickly. So it seems that you need new ideas in order to get adaptive lower bounds.
Thank you.
Does anyone else have any question? Okay, then let's thank Avishay again for the wonderful talk.
Thank you.